2 more minutes to finish your reading. Come back to me now. I hope that was enough time to finish up at least the basic part of the reading. Give me a 2 facts that you guys learned. Let's go with wireless group. Something that you guys saw that was represented. Anything will work here. So nonpolar covalent bond by a diatomic, but why is it nonpolar? Okay. So similar electronegativities yield equal sharing of electrons between the covalent bond, nonpolar covalent bond. Kirk, something else, or Kirk's group.
An atom can have dipoles, but not be a dipole.
Okay, so a molecule can have dipole moments within the molecule, but not be overall polar. Okay, have a dipole, but why? Or how does that work?
Looks like the electrons may be attracted away from the central atom. But as long as it's happening in all directions, like the molecule itself.
Because it cancels out the polar components. Okay, so the example regarding that was carbon dioxide, and I thought this was so cute. I had to show you guys this today. I honors chemist read this today too. So this penguin versus the polar bear, in this case hydrochloric acid, shows the H fluorine bond being polar, which is indicated by that dipole moment. As I think Levi's group showed us when they did their electronegativity discussion. We're pointing towards the more what? What's the arrow pointing towards? The more electronegative element of the bonding situation, right? And overall, since there's no cancellation, so there's not one dipole moment pointing to the left and one pointing to the right, because there's no negating of the dipole moments, overall the molecule is polar, which is why it says the molecule additionally also has a dipole component as well. But then the carbon dioxide, C to O versus C to O, both of those are polar bonds, or polar covalent bonds. Who's more electronegative within the bond? Oxygen. In both accounts, oxygen and oxygen are both pulling the electrons in the bonded pairs towards themselves, but there's equal pull on both sides, so overall it cancels out the entire dipole moment, creating a molecule that's nonpolar. So when we say polar, you must follow it up with polar molecule or polar bond, or nonpolar molecule or nonpolar bond. That way we're knowing what we're talking about, okay? So that whole idea gives you some reasoning behind it, but then we're going to kind of draw our own structures and label your structures on your lab. This is water. We all knew water was polar, but why in this case, what's controlling this to be overall nonpolar and this to be polar? Shape. So geometry, molecular geometry specifically, plays a huge role in trying to figure out if it's polar or nonpolar. That's why we did all the geometry stuff first before we tackle the polarity, the molecular polarity. All right, so work with me here. I'm going to find my appropriate slide. Yes, ma'am?
Do a lot of electrons share, change the electronegativity of polarity?
Can the bond polarity change the, say that one more time?
So So like say that there's like a double bond. Say it's like a resin structure with like a double bond on one side.
Okay.
So would that make it non-polar or does that look
I will say, because you consider them to be a superimposed kind of blended shape, not a one or the other, it would have to be equal on both sides, so it would probably be non-polar, but it would depend on what the atoms were too. So I'm thinking ozone, like we did yesterday, that's non-polar. Oh, no, actually, that's polar because it has a lone pair on top, which causes it to be bent. It's more about the shape too. Yeah, so that's what I'm going to talk about now, okay? So I think I'll clear up some answers today. So please write down something for yourself today, whether it's you're writing in labeling examples I'm doing, or you're writing down some additional notes for yourself. Just listening for me not today is not going to work. So this is something we've already spoken of a lot about. So the Vesper theory, valence shell, say the rest of it, electron pair repulsion. We talked about the lone pairs taking up a lot of space. Generally, if you expanded octet, where are the lone pairs at? Equatorial region, use your vocabulary. Think equatorial has the most space, it's got 120 degrees around them. Axial takes up, it's going to have a 90-degree angle between them, so it creates a lot of repulsion, and that's what you're following up with your lab on, is the repulsive units. So you're going to try to determine the molecular arrangement visually now. You have to draw your, the first step, if you do not count your valence electrons, it's very difficult to know if you have the correct number of valence electrons on your structure. That's why you have to count them first. And after your structure's been drawn, and after you've considered where your lone pairs are, you consider the molecular geometry. So we have a plethora. We have like 11 or 12 options for molecular geometry. In seesaw, where's the lone pair? You say on the top, but give me axial or equatorial. Are we having a hard time visualizing that? What's the, okay, go back, seesaw. What's the electron group geometry? Okay, but hold on, follow up. What's that answer first, then we'll come back to that. It's trigonal bipyramidal. Okay, so we've got axial, and then we've got our equatorial areas. That kind of looks like a triangle, doesn't it? Yeah, okay. So if that's my 5 locations, where is my lone pair? No, it cannot be axial, guys. Those are 90. They can't take on a 90-degree angle. It's too much repulsion. Levi, you just told me this. Where's my lone pair? It's got to be on the equatorial plane because you've got a place here, here, and here. Those are all in the equatorial region. What angle are they apart from each other? 120. Okay, so we're really working on visualizing this. 120 versus another 120 versus another 120. You're going to put your lone pair there because it takes up the most space. It does not want to be, if at all possible, 90 degrees with anything. Now I understand it's going to be 90 with that top axial and the bottom axial, but it's much better than being 90 with another lone pair, or more 90s than it needs to be. So try to really put them equatorial. And so it doesn't matter how you draw it. I think many of you guys drew it like this, sulfur hexafluoride. Something like that. And you drew it like this, and to me, I mean, I know kind of what you mean, and you know that it seesaws back and forth, but you're going to visualize that being axial. But you need to always put them upright and think about axial versus equatorial, and then if you continue to draw it in one way, maybe it'll make more sense. Stick with what's best for you, but definitely flip that up and make that look like you know it looks. I'll draw it like this, and then lone pair here. Maybe that'll make more sense. So as you're drawing, maybe think about the shapes you think they're starting to take on. That way you kind of mesh your thoughts together. Okay. So we watched that video yesterday. We talked about the 5 domain electron geometries. There's not too many to choose from. What are the bond angles in linear? 180. What's the bond angle in trigonal planar? 120, because you're thinking planar, triangle, 360 divided by 3. Tetrahedral, 109.5, or drop it, 107 or 104.5. That's really about it. And that sequentially is taking one of the ligands and making a lone pair. Another ligand off, lone pair. And so that creates more repulsion, which creates a shorter or smaller bond angle. Trigonal bipyramidal angles, right, 120 between the equatorial region and 90 between the axial and equatorial. Okay, octahedral, 90 all the way. You see how I'm saying the bond angles are consistent. There's not a whole lot of wiggle room. Of course, if we had some sea salt or T-shaped, we might have a little less than 120, or a little less than 180, but it's still approximately that. Okay, so we kind of did this right now. I'm going to talk about delocalized electrons in a second. So polarity, and you guys just read the comic. I'm trying to show my people at home. They can see this on my website. So you guys just read the comic to see how bond polarity influences molecular polarity, but it does depend on the shape as well. So you're looking for the entire molecule's shape and then trying to figure out, does one side of the molecule have a higher electronegativity, which created some sort of partial negative charge, versus the other side, which has a lower electronegativity, which created additionally a lack of electrons, hence a partial positive charge. So slightly positive and slightly negative is how we refer to the locations of electron distribution. And we call that a partial positive like that. It's like almost an 8, it's a lowercase sigma, and a partial negative. So when we do find a molecule is polar, we call it polar, so polar molecule. We say it overall has a dipole moment. And I'll demonstrate that with you for water in just a second. So we can say it's said to be dipolar. That just sounds weird. Usually we just say it's polar, and it has a dipole moment. And this is what my group, my electronegativity group, talked about, how the units of polarity are described as debye, D-E-Y, or D-E-B, debye, yeah, D-E-B-Y-E. And it's actually a accumulation of the distance that the polar bond kind of takes place over, and the charge that is distributed over that bond. The charge is caused by electrons being in one place or another. So that C is for coulombs meters, so it's called a coulomb meter. And we will never have to calculate debyes, but they will give you data. And the data you have to analyze to say, oh, it's really polar, or it's not so polar, and they'll give it to you in units of debye units. And so if you see something like debyes or coulomb meters, you're really looking for magnitude differences, not actual calculations yourself. And I'll show you an example in a second. So everybody go through your entire process of drawing ammonia. What's the formula for ammonia? And make sure, wasn't this one on your lab? Or no, I gave you nitrogen trichloride, the trifluoride. Okay, let's do that instead. Nitrogen, what was it, trichloride or fluoride?
Fluoride.
Fluoride, okay. So I'm trying to do this so that you can get on with your lab as well. So I know your first step is to do what? Say again? Count the valence electrons. So 5 plus 21 is 26 valence electrons. And then you choose your central, and then you draw ligands. And I'm drawing it in a T-shape, but is this T-shaped? No, T-shape goes with expanded octet. And then I've got how many valence electrons here? At this point, 6. And then you octet them all up. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. How many electrons are in my structure entirely right now? 24. So then where do I pop on the extras? Central atom, because first it doesn't have octet, and second, that's where you plop your extras if you have them. So I can see that I've got 3 ligands and 1 lone pair. 3 ligands, 1 lone pair. It wants to be, and we already know in electron group geometry, what's the structure? Electron group. Say again? It's tetrahedral. Okay, so it wants to be at what angle apart from each other? 1 and 9.5. It wants to be. But then that lone pair is repelling all the bonded pairs, just squish them together a little bit more. So what's the true bond? 107. And what's the molecular geometry? Say again? Trigonal. Say again? This lone pair is at the top, pushing the legs down.
The molecular string in the middle.
It's just a pyramid. It's not 2 pyramids, it's 1 pyramid. Right? It's just 1 pyramid. So trigonal pyramidal with a bonding of 107. So now let's consider the electronegativity differences, which is what your homework was. So I will check over some of that, but I also know that you can check the answers in the back of the book. That's why I wanted you to do electronegativity before you finish class. Who's more electronegative, nitrogen or chlorine? You guys know this? Okay, so chlorine is more electronegative. It's got a smaller atom, higher Z, yada yada. Okay, so draw an arrow pointing towards the chlorine and put a hash mark on the side that's closer to nitrogen. That's showing us that there's a dipole moment on this covalent bond from the nitrogen to the chlorine. And that happens over and over again because there are 3 identical bonds between nitrogen and chlorine. So what does that mean we're doing with the electrons of this covalent bond?
We're gonna pull forward.
Right, they're being pulled towards the chlorine, pulled towards the chlorine, pulled towards the chlorine. So essentially, I'm going to put like a little globe here. Okay, so west, south, and east, I have a partial negative, partial negative, partial negative charge. Not because of the lone pairs here per se, but because of the shift of electrons towards the perimeter. So far, so good? Yay, nay? Yay, okay. So additionally, that leaves the partial negatives going down low. But then we know that there's this pyramid structure here. So there's a huge partial negative. I'm going to put 2 partial negatives up top because of the lone pair structure, or the lone pair feature at the top of this pyramid. So overall, this was a difficult one, and that's why I wanted to use, because this was in your lab, you have to tell me polarity. I would suggest this would be a polar molecule, simply because, yes, I see there's a partial negative, partial negative, partial negative, and partial negative, so it looks like there's a good partial negative all over my globe, but there's a higher magnitude of the partial negative up top because the structure being having a lone pair at the tippy top of this pyramid. The lesser of a negative, or distribution of negatives, down below. But you'd have to have more data to actually support that. So what would be some things that we could see? You could see a high attraction between nitrogen trichloride and another nitrogen trichloride. And if it has a high attraction, it could very well indicate as polar, which gets us into intermolecular forces. So you're going to consider the bond geometry, or the bond polarities, and the geometry to consider, is this molecule polar or not? But let's do another one for your lab, okay? You guys choose one, and which one is what you want me to do? Xenon difluoride. So, and so basically it looks like that, right? Okay, so this one's weird because xenon doesn't have a true electronegativity. It's kind of high, and so is fluorine. So you have to guesstimate on some of these in honors chem. You guys got the electronegativity sheet. In AP Chem, you have to know there's relative differences here. Low electronegativity for the metals, high electronegativity for the non-metals, and there's some in between. So I would say in our equatorial region, we have an equal amount of electron distribution, and fluorine, which is the most electronegative element on the periodic table, is helium electronegative? No, it's got duet, it's totally fine. Neon?
No.
No. Argon? No, those all have zeros. Krypton, xenon, and radon, they start to pick up some electronegativity because they're huge and they can actually take on additional electrons. But there's an equal distribution of electrons here, and if it were, and it probably is, a polar covalent bond pointing up and a polar covalent bond pointing down, these 2 dipoles offset each other. They cancel each other out. And these 3 negatives cancel each other out because they're equally distributed. So you have equal electron distribution, and the dipole moments cancel each other out. So overall, what would you guys say? Non-polar overall. And so if you're non-polar, molecule, what kind of intermolecular force can you have? Just seeing if we remember this. London dispersion forces are what you would undergo with another molecule. All right, let me do one more, because you guys are going to have to do the rest of these, okay? Can I take a hard one off your plate? It's your choice. Okay, the RF5 shape is a square pyramidal. So I'm drawing these as a kind of structure to give you the indication of how it looks. Assume those are all offsets, right? Okay, lone pair. All right, that's our square pyramid, right? it's octahedral in electron group geometry because of the additional electron lone pair. Overall, same dipole moment. Who's the most electronegative, bromine or fluorine? Fluorine. So if anything, we could point the bond polarities out to fluorine on all of these to show that the electrons are being pushed to the perimeter and up. But then we've got this honking lone pair down here. So do you think that this lone pair is going to be offset by this slightly polar bond? No. Okay. So the lone pair is not offset by this by this slightly polar covalent bond. So difference is here. This one down here is going to have a higher partial negative charge. I'll just put two of those there because there's two electrons, versus all of this up here, which is somewhat partial negative, but not nearly the magnitude of the lone pair. So there's an unequal distribution of electrons, polar and nonpolar. Polar. If there's an unequal distribution of electrons, it is a polar molecule, point blank. Now, some of those are hard to figure out, though, but I want you to consider like the opposite forces. Yeah.
Do the four on the equatorial plane cancel each other out?
Yes, they cancel each other out because they're equally pulling left, right. Opposite directions. Like this one cancels with this one, and this one cancels with this one. Okay, opposite forces. So what kind of intermolecular force would this one undergo? We have two other options, dipole-dipole and hydrogen bonding. Dipole-dipole. All right, speaking of this, I had two other assignments for today, so let me see where I actually need to go here. I don't think we need that. We just talked about that. Oh, this is a good diagram of seeing how the dipole forces cancel each other out. So this is a linear structure, cancel each other out. 120s cancel each other out. And tetrahedral, they're all the same bond, can also cancel each other out because they're all pulling in not exactly opposite directions, but opposite enough to be considered cancellation is occurring. So those are some of the easy ones that are the non-expanded octets. Do you guys feel that you could try to do that, polarity? I need to kind of give you guys a chance to do that. All right, so my last assignment, this was all the same stuff. I'm going to skip this for now. We'll do the intermolecular forces jigsaw. In 2 days, you guys will work together to talk about intermolecular forces before I teach them. So, and some of this is background knowledge, but if you go under if you want to pull this up on your phone right now, I have 10 minutes left in class, so I want to go ahead and assign this today. So under homework, where did I put that? Nope. Well, let me just pull this up on my website. So under AP Chem homework all the way down, it says February, oops, refresh this. Refresh it for yourself, guys. Intermolecular forces jigsaw. So intermolecular forces jigsaw is going to have you guys work with expert groups to learn enough about one of the intermolecular forces. We're only going to do 3: London dispersion forces, dipole-dipole, and hydrogen bonding, and I'll do the other one for you guys. And you're going to work in groups of 3. No, I'm sorry. We have to work in 3 big groups. We almost have 3 big groups. Can one of you guys go this way and 3 of you guys go that way? Yeah, yeah, this is this group right here, so I'm just going to split you guys. And when we get there, okay? And I'll pull Avery and Archie into those. So you're going to work in kind of like base areas as a hydrogen bond, London dispersion, or dipole-dipole. You're going to learn everything you can about that. And some of the questions are going to be like, on your, as you can see, illustrate what does your intermolecular force look like, type of attraction, is it going to be based on, is it weak, strong, or in between, what types of substances would this occur in, kind of like the basics of everything, and then I'll kind of go into the extra details. But I give you the expert group information in resources, and then the questions are right below. So I'm going to go ahead and assign Rushi. Your group will be group 1 dipole-dipole. Back group will be expert group hydrogen bonding. And then this group over here, which whoever ends up being over here as well, will be London dispersion. Okay? So at that point, this is your expert group. You guys will know everything you need to know about that. And at the end, we'll come back into groups of 3. I'll pull one person from dipole-dipole, one from hydrogen bonding, and one from London. And you guys will share what you learned. So it's not a group activity at the end. It's going to be an independent activity at the end because you guys you'll be experts in your field. Okay? So I'm recommending some sort of poster to go along with this because you're going to want to show visuals. So go ahead and read some of that. If you guys need to start looking at some information, you guys have about 10 minutes right now. If you want to pull up a computer, but I'm going to show you first from my computer, okay? You guys are with me for innovation, so if you want to pull up a computer, So 1, 2, 3, you guys are there. Please read the instructions thoroughly. I went over that really quick.